Everything you thought you knew about the beginning is wrong. Not slightly incorrect, not somewhat misunderstood, but fundamentally, catastrophically, beautifully wrong. For nearly a century, we've told ourselves a comfortable story about cosmic origins, a tale so elegant and complete that it felt like truth itself. The universe began with a bang, we said. Before that, nothing. Literally nothing. No space, no time, no possibility of anything. The question itself was meaningless, like asking what's north of the North Pole. Case closed, mystery solved, sleep well. But what if the case was never really closed at all? What if the mystery was only just beginning? In laboratories scattered across the globe, in the silent watches of space telescopes, in the intricate mathematics scratched across blackboards, in windowless rooms, something extraordinary has been unfolding. Scientists have been discovering anomalies, patterns, whispers of something that shouldn't exist, echoes before the echo, signatures of a time that wasn't supposed to be. The data doesn't just challenge our understanding, it demolishes it. It rebuilds it. It forces us to confront a question we thought we'd forbidden ourselves from asking. What came before the Big Bang? The answer, it turns out, might be everything. Think about time for a moment. Really think about it. We experience it as a river, flowing from past to future, carrying us along its inevitable current. We measure it with clocks, mark it with calendars, feel it in the ache of aging bones and the growth of children into adults. Time seems as fundamental to reality as reality itself. It's the stage upon which every drama unfolds, the canvas upon which every moment is painted. Remove time, and you remove existence. At least, that's what we thought. The traditional story of cosmic genesis begins approximately 13.8 billion years ago, though even that number has been refined and re-refined as our instruments grow more sensitive, our calculations more precise. At that moment, which we call the Big Bang, everything that exists came into being. Not just matter and energy, but the very fabric of space-time itself. The universe didn't birth into space, space was born with it. The universe didn't begin at a moment in time, time itself began at that moment. Picture it if you can, though the human mind wasn't designed for such comprehension. All the matter in all the galaxies, all the energy that powers every star, all the space between every atom, compressed into a region smaller than the smallest thing you can imagine. Smaller than a grain of sand, smaller than a single atom, smaller than anything. A point of infinite density, infinite temperature, infinite everything. A singularity. And then, in an instant that might have been no time at all or all time at once, it exploded outward. But not like a bomb exploding into air. There was no air. There was no into. The explosion was space itself expanding, carrying infant matter and energy along for the ride. In the first fraction of a second, the universe inflated faster than light itself could travel, though this doesn't violate physics, because space itself was expanding, not objects moving through space. It's a crucial distinction, one that trips up even the careful thinker. Within the first second, the universe cooled enough for fundamental particles to form. Quarks and electrons materialized out of the seething energy, like islands emerging from a boiling ocean. Within minutes, those quarks fused into the first atomic nuclei, primarily hydrogen and helium, the simplest elements, the building blocks from which everything else would eventually be constructed. Stars, planets, people, thoughts, dreams, all of it traced back to those first few minutes. For hundreds of thousands of years, the universe remained too hot for atoms to form. Electrons zipped around freely, constantly colliding with photons. Light unable to travel more than a tiny distance before bouncing off yet another charged particle.
The universe was opaque, a glowing fog. But as expansion continued and temperature dropped, electrons finally settled down around nuclei, forming the first atoms. Light could travel freely at last. That ancient light still reaches us today, stretched by cosmic expansion into microwaves, forming what we call the cosmic microwave background radiation. It's the afterglow of creation, the oldest light in the universe, a baby picture of reality itself. This story, elegant and awe-inspiring, was revolutionary when it emerged. It united observations from across physics and astronomy into one coherent narrative. Edwin Hubble's discovery that galaxies were racing away from each other. The abundance of light elements matching predictions from nuclear physics. The cosmic microwave background, discovered accidentally by two engineers who thought the hiss in their antenna was just pigeon droppings. Everything fit. Everything made sense. The universe had a birthday, and we could calculate it. But there was always a problem lurking at the heart of this beautiful theory. What about before? Scientists initially dismissed the question. They built walls around it, declared it off-limits, stamped it with metaphysics, not physics. Augustine of Hippo, that ancient theologian, had said something similar about God's creation. Asking what came before creation was meaningless because time itself was created. Before time, there was no before. The logic seemed airtight. Close the box, move along. Yet questions don't disappear just because we declare them unanswerable. They fester, they whisper, they grow. Physicists, despite their protestations, couldn't help but wonder. In quiet moments, in the spaces between equations, the question returned. What came before? Was there really nothing? And if there was nothing, how did something emerge from it? Can nothing even exist? What would nothing look like, feel like, be like? Here's where the story begins to crack open, where the comfortable narrative starts to crumble like ancient parchment. Because nothing, it turns out, is far more complicated than anyone imagined. In the quantum realm, that strange domain of the very small where normal rules break down and probability reigns supreme, nothing isn't empty. It seethes with activity, it boils with potential. Virtual particles pop into and out of existence, borrowing energy from the universe and paying it back so quickly that they leave no trace, no ledger entry, no permanent mark. They exist and don't exist simultaneously, hovering in superposition between being and non-being. This isn't speculation or philosophy, it's measurable, testable, real. The Casimir effect demonstrates it beautifully. Place two metal plates extremely close together in a vacuum, and they're pushed together by an invisible force. Why? Because the quantum foam between them can only support certain wavelengths of virtual particles, while the space outside the plates can support all wavelengths. The imbalance creates pressure. Nothing, apparently, can push. So if nothing can do that, what else can it do? Could nothing, given the right conditions, create everything? Could a quantum fluctuation, borrowing an immense amount of energy for an immeasurably brief moment, birth an entire universe? The mathematics suggested it was possible. Not just possible, inevitable. Given infinite time or infinite space, every quantum possibility becomes reality somewhere, somewhen. But this answer, provocative as it was, still required something. It required quantum mechanics. It required the laws of physics. It required space-time, even if that space-time was about to be born. Where did those come from? You can't pull yourself up by your own bootstraps. You can't create the rules using the rules that don't yet exist. The question remained, transformed, but not answered. What came before the before? For decades, this seemed like the end of the line. The Big Bang was our creation myth, complete with its own mystery of ultimate origins, its own forbidden question, its own sacred unknowability. We could calculate back to the first fraction of a second, but that last moment, that singularity, remained stubbornly inaccessible. Our equations broke down. They produced infinities, meaningless results, mathematical gibberish. The singularity was a wall, a barrier, a sign reading, beyond this point, physics does not apply. But what if the singularity never existed? What if it was an illusion, a mathematical artifact, a mirage created by applying the wrong theories to extreme conditions? What if we had been staring at the problem through the wrong lens all along? Enter the rebels, the questioners, the physicists who refuse to accept that the universe's origin story should contain its own built-in mystery, its own explanatory black hole. They came armed with new mathematics, new theories, new ways of understanding reality at its most fundamental level. They came with quantum mechanics married to gravity, with strings vibrating in 11 dimensions, with loops of space-time woven into networks. They came with different answers, contradictory answers, proliferating answers.
And slowly, piece by piece, observation by observation, a new picture began to emerge. Not a single picture, perhaps, but a gallery of possibilities, each strange in its own way, each challenging in its own right, each offering a glimpse beyond the Big Bang into territory we'd forbidden ourselves from exploring. One of the most radical suggestions came from the application of quantum mechanics to the universe itself. If quantum mechanics governs the behavior of tiny particles, why shouldn't it govern the behavior of the entire cosmos? True, we never see quantum effects at large scales. A baseball doesn't exist in multiple positions simultaneously. A cat is either alive or dead, whatever Schrödinger might have proposed in his famous thought experiment. But perhaps that's because large objects interact with their environment too much, too quickly, collapsing their quantum states into classical certainty. The very early universe, though, was different. It was tiny, smaller than an atom, smaller than a quark, perhaps smaller than anything. At that scale, quantum mechanics rules absolutely. The universe itself might have existed in a superposition of states, neither existing nor not existing, hovering between being and nothingness. In this view, the Big Bang wasn't a beginning, it was a quantum transition, a probabilistic flip from one state to another. The universe didn't come from nothing. It came from a quantum state that included the possibility of both nothing and something, and it chose something. Think about that for a moment. Sit with it. The universe might have chosen to exist, not through any conscious will or divine intention, but through the blind mathematics of quantum mechanics. The same mathematics that governs which slit an electron passes through in the famous double-slit experiment. Existence might be a quantum event, as random and inevitable as radioactive decay, as strange and natural as entanglement. But quantum mechanics isn't the only rebel in this story. Another challenge came from an unexpected direction: the mathematics of space itself. Einstein had shown that space and time weren't static, unchanging backdrops against which events occurred. They were dynamic, malleable, responsive to the presence of matter and energy. Mass curved space-time, and that curvature was what we experienced as gravity. The equations were beautiful, precise, verified by countless experiments and observations. They described the universe at large scales with stunning accuracy. But Einstein's equations, like all equations built on continuous mathematics, broke down at singularities. Division by zero. Infinities erupting from the calculations like mathematical demons. The Big Bang's singularity was one such problem child. Black holes contained others. Anywhere that density became infinite, the equations threw up their hands and surrendered. Something was missing. Something fundamental. What if space and time weren't infinitely divisible? What if they came in discrete chunks, tiny beyond tiny, but finite nonetheless? Just as matter is made of atoms, energy comes in quanta. Perhaps space-time itself had a granular structure, a minimum unit beyond which further division was meaningless. This was the insight behind loop quantum gravity, one of the major competitors to string theory in the race to unify quantum mechanics with general relativity. In loop quantum gravity, space-time is woven from tiny loops, connected into a vast network like cosmic chainmail. These loops are incomprehensibly small, operating at the Planck scale, about 10 to the negative 35 meters. That's small enough that if you enlarged an atom to the size of the observable universe, the Planck scale would still be smaller than an atom. At that scale, the smooth fabric of space-time that Einstein described becomes grainy, discontinuous, quantum. And here's where it gets interesting. If space is made of these discrete loops, then density can't become infinite. There's a limit. As you compress matter into a smaller and smaller region, as you rewind the expansion of the universe back towards its supposed beginning, something unexpected happens. Instead of collapsing into a singularity, the universe bounces. Like a rubber ball compressed to its limit and then springing back, the universe reaches a maximum density and rebounds. The Big Bang in this view was a big bounce. A bounce. Not a beginning, but a transition. A moment of maximum compression followed by expansion, perhaps one in an endless series of compressions and expansions, contractions and releases, like the universe breathing, in and out, forever. This opens up an entirely new vista. If the Big Bang was a bounce, then there was something before it. There was a previous universe, contracting, collapsing, compressing down to the bounce point, and then exploding outward into our universe. That previous universe had stars and galaxies, planets, and perhaps even life. It had its own history, its own story, stretching back through time. And before that universe, another bounce. And before that, another. Turtles all the way down, except instead of turtles, it's universes, and instead of down, it's backward through eternal time.
But wait, hold on. Let's think about this carefully. If there was a previous universe that collapsed and bounced into ours, what information passed through the bounce? Could structures, patterns, knowledge somehow survive the compression and re-expansion? Or was everything erased, reset, the cosmic slate wiped clean? This is where the newest research becomes tantalizing. The data starts to whisper secrets. Scientists analyzing the cosmic microwave background, that ancient light from the early universe, have found anomalies, patterns that shouldn't be there, cold spots, asymmetries, statistical fluctuations that seem to suggest large-scale structures, correlations across vast distances that standard Big Bang theory struggles to explain. Could these be echoes, remnants, fossilized patterns from before the bounce, somehow preserved through the transition like footprints in concrete that hardens? Some researchers think so. They've run simulations, crunched the numbers, analyzed the data. The signals are weak, ambiguous, subject to multiple interpretations. But they're there. They're real. And they're telling us something. What they're telling us might be revolutionary. If information can pass through the bounce, then our universe isn't isolated.
It's connected to what came before. We're not the first chapter in the book of reality. We're the latest chapter in an endless story, with previous chapters we can potentially read if we develop the right instruments, ask the right questions, look in the right places. Think about what that means. Really think about it. The atoms in your body, the particles that make up every cell, every molecule, every thought in your brain, might have existed before the Big Bang. Not in their current form, obviously. They were torn apart and reconstructed. But the fundamental constituents, the quantum fields from which particles emerge, the deep mathematical structure of reality itself, persisted. You are made of pre-Big Bang material. You are older than the universe. But the bouncing universe model isn't the only game in town. Other theories offer different perspectives, different possibilities, different ways to sneak around the singularity and peer beyond it. One of the most mind-bending comes from eternal inflation, a theory that takes the inflationary period of the early universe and extends it, multiplies it, fractally reproduces it across an endless landscape of reality. Here's the idea. The rapid expansion that occurred in the first fraction of a second after the Big Bang wasn't a one-time event. It's still happening, right now, in other regions of reality far beyond our cosmic horizon. Our entire observable universe, all 100 billion galaxies, all trillion stars, all vast gulfs of space between them, is just one bubble in an infinite foam of universes. Each bubble its own Big Bang, each bubble expanding, creating space and time within itself. In this view, the Big Bang wasn't the beginning of everything. It was the beginning of our local region, our cosmic bubble. Beyond our bubble, the eternal inflation continues, spawning new bubbles constantly, has been spawning them forever, will continue spawning them eternally. There was no first bubble. There will be no last bubble. The multiverse is eternal, boundless, infinite in both space and time. What came before our Big Bang? Other Big Bangs, countless other Big Bangs, an infinity of them, each creating its own universe with its own laws of physics, its own fundamental constants, its own possibilities for life and structure and complexity. Most of these universes would be sterile, lifeless, unable to support anything interesting. The constants would be wrong, gravity too strong or too weak, electromagnetism cranked up too high or turned down too low. But in an infinity of universes, everything that can happen does happen, including universes like ours, where the constants are just right, where stars can form, and planets can coalesce, and life can emerge and wonder about its origins.
This is the anthropic principle in its most extreme form. We observe a universe compatible with our existence not because the universe was designed for us, but because only in such a universe could observers like us exist to do the observing. In all the other universes, in all the other bubbles, with all their different physical laws, there's nobody to notice that they exist. We're selection bias made cosmic. We exist in a habitable universe because uninhabitable universes don't get observed. It's an intellectually satisfying answer in some ways. It explains why our universe seems so finely tuned for life, why the constants have the values they do, why we're here at all. We're here because we're in one of the rare bubbles where here is possible. Simple, elegant, complete, but deeply unsatisfying in other ways. It turns the question, why, into an accident of probability. It makes our universe, our very existence, fundamentally random, one outcome among infinite outcomes, special to us, but meaningless in the grand scheme. It also makes the theory nearly untestable. How do you observe other universes when they're forever beyond our cosmic horizon?
separated from us by eternally inflating space that's expanding faster than light can cross it. Yet even here, the data has started to offer hints. Those same anomalies in the cosmic microwave background that might be echoes from a bouncing universe could also be something else. They could be bruises, scars, evidence of collisions between our bubble and neighboring bubbles in the early moments of our universe's formation. If two bubbles touched, merged, collided, the impact would leave a distinctive pattern, a signature written in the temperature fluctuations of the ancient light. Several research groups have claimed to find such patterns. Others dispute them. The debate rages. The data remains ambiguous. But the fact that we can even have this debate, that we can look for evidence of other universes in our sky, is extraordinary. 10 years ago, 20 years ago, the multiverse was pure speculation, philosophy dressed in mathematical clothing. Now it's at least potentially testable. The data might tell us if we're alone or part of something vastly larger. The universe itself might testify about its own origins, its own context, its own place in a greater reality. And then there's string theory, that controversial, beautiful, frustrating attempt to unify all of physics into one elegant mathematical framework. In string theory, the fundamental constituents of reality aren't point particles, but tiny vibrating strings. Different vibrational patterns correspond to different particles. An electron is a string vibrating one way. A quark is the same string vibrating differently. Even gravity, that stubborn force that resisted quantization for so long, emerges naturally from string vibrations. But string theory comes with a price. It requires extra dimensions. Not the 3 spatial dimensions and 1 time dimension we experience, but 10 or 11 dimensions total, depending on which version of the theory you're working with. Where are these extra dimensions? Curled up, folded, compactified into shapes so small we can't detect them directly. Imagine a garden hose. From far away, it looks one-dimensional, a line. Up close, you see it's actually two-dimensional, a tube with circumference as well as length. The extra dimensions of string theory are like that, but curled up at the Planck scale, invisible to everything except the strings themselves. These extra dimensions open up new possibilities for cosmic origins. Perhaps our 4-dimensional universe is embedded in a higher dimensional space, what string theorists call the bulk. Our Big Bang might have been caused by events in the bulk, interactions between higher dimensional objects called branes, short for membranes. Imagine 2 branes floating in the bulk, drifting toward each other, colliding. The energy of the collision creates a universe on one of the branes. That universe is ours. The collision is our Big Bang. In this picture, time extends backwards before our Big Bang, but not in our universe. Time was passing in the bulk. The branes were moving, and then they collided, and our space-time came into being, fully formed, the product of a higher dimensional event. What came before the Big Bang? Higher dimensional physics, brain dynamics, a cosmos we can barely imagine, let alone observe. Or perhaps the extra dimensions offer another path entirely. Some versions of string theory suggest that the universe undergoes cycles, expanding and contracting, but not in the simple way of the bouncing cosmology. Instead, the extra dimensions themselves expand and contract. Our familiar 3 dimensions might grow while others shrink, then reverse, creating an endless cycle of exchange, a cosmic breathing that manifests in our experience as alternating big bangs and big crunches.
The mathematics of all this is staggering in its complexity. The equations fill textbooks, the calculations require computers, the conceptual framework demands years of study to even begin to understand. Yet, at its heart, string theory is trying to answer the simplest questions. What is reality made of? How does it work? Where did it come from? And increasingly, string theory is making contact with observation. Not direct observation of strings, which may be forever impossible given their tiny size, but indirect effects, subtle consequences that might show up in particle physics experiments, cosmological observations, gravitational wave detectors. The theory is slowly, grudgingly becoming testable. Not as testable as physicists would like, but more testable than it was.
Here's a thought that should make you pause. Should make you set down whatever you're doing and stare into space for a while. All of these theories, different as they are, incompatible as they might be, agree on one fundamental point. The Big Bang was not the beginning. Something came before. Always, inevitably, necessarily. The singularity, that mathematical monster that haunted physics for decades, was a phantom, an illusion, a sign that we were asking the wrong questions with the wrong tools. Reality, it seems, is far older than we imagined. Not 13.8 billion years old, but perhaps infinitely old, eternal, boundless in time as well as space. Our universe, vast as it is, ancient as it seems, is just a moment in an endless story, a single frame in an infinite film, a brief chapter in a book with no first page. Does this diminish us? Make us smaller? More insignificant? One could see it that way. Our cosmic importance shrinks with each conceptual revolution. First, we lost our place at the center of the solar system. Then we discovered our solar system was one among billions in our galaxy. Then we found our galaxy was one among billions in the universe. Now we're learning our universe might be one among infinite universes, and our Big Bang might be one among infinite Big Bangs. We're not special. We're not central. We're not even particularly unusual. But there's another way to see it, a better way, perhaps. We're connected. We're part of something vast, ancient, complex beyond comprehension. The stuff of our bodies, the thoughts in our minds, the love we feel and the art we create, all of it is woven into the deepest fabric of reality. We're not separate from the cosmos. We're how the cosmos knows itself. We're how infinity becomes aware of its own existence. Every atom in your body was forged in the heart of a dying star, scattered into space, gathered into a cloud of gas, collapsed into a new star and planets, and eventually assembled into you. But now we know the story goes back further. Those atoms existed in some form before the Big Bang, carried through the bounce, or birthed from the quantum foam, or erupting from the brain collision. You are literally made of eternity. Your constituent parts have existed forever and will exist forever, changing form but never truly disappearing. Think about that the next time you look up at the night sky. Those stars, those galaxies, that vast darkness between them, all of it is your relatives, your family, your siblings in deep time. The same quantum fields that vibrate to produce the electrons in your neurons also vibrate to produce the quarks in neutron stars, the photons streaming from distant quasars, the dark matter holding galaxies together. It's all one thing, one unified field, one reality expressing itself in infinite variety. But let's return to the data, because that's where the story becomes concrete, where speculation meets observation, where theory faces its ultimate test.
What exactly have scientists found that suggests something came before the Big Bang? The cosmic microwave background radiation is our primary window into the early universe. It's been mapped with exquisite precision by satellites like COBE, WMAP, and most recently, Planck. These maps show us the temperature of the radiation across the entire sky, accurate to millionths of a degree. And mostly, the maps show exactly what standard Big Bang theory predicts. Small random fluctuations in temperature, the seeds of future galaxies, distributed in a pattern that matches quantum mechanical predictions perfectly. But not quite perfectly. There are anomalies, small deviations from what the simplest models predict. The famous cold spot, for instance, a region of the sky that's slightly cooler than it should be, larger than it should be. Unlikely, but not impossible according to standard theory. Except when you calculate just how unlikely, the numbers start to look suspicious. It's not just improbable, it's remarkably improbable. Like flipping a coin and getting heads 100 times in a row. Possible, yes. Likely, no. Some researchers suggest this cold spot could be a bruise from a collision with another bubble universe. The impact would create a pattern of cooling, a distinctive signature. The mathematics works, the signature matches, sort of. Other researchers are skeptical, suggesting the anomaly is just statistical noise, the kind of thing you expect to find if you analyze enough data. The debate continues.
Then there's the matter of asymmetry. The cosmic microwave background should be symmetric, or very nearly so. The universe expanded uniformly in all directions, after all. Quantum fluctuations should be randomly distributed, showing no preferred direction. Yet some analyses suggest a slight asymmetry, a hemispherical variation, one side of the sky subtly different from the other. This shouldn't exist. There's no explanation for it in standard cosmology. Unless perhaps it's a remnant from before the Big Bang, a directional signal carried through the bounce or impressed during the brain collision, or leaked from a neighboring bubble universe. Other anomalies have been reported over the years. Rings in the cosmic microwave background that might be signatures of violent events in a previous universe. Patterns suggesting large-scale structures beyond our cosmic horizon, impossible in standard Big Bang cosmology, but potentially explainable if our universe is embedded in something larger. Most of these signals are controversial. Many don't survive independent analysis, but taken together, they hint at something. They suggest our story of cosmic origins might be incomplete. Gravitational wave astronomy offers another window, newly opened. When LIGO detected the first gravitational waves from colliding black holes, it opened up an entirely new way of observing the universe. Gravitational waves pass through matter almost without interaction, carrying information across cosmic distances without distortion. They could, potentially, carry information from before the Big Bang. Some theoretical work suggest that a bouncing universe would produce a distinctive gravitational wave background, different from what we'd expect in standard Big Bang cosmology. Future gravitational wave detectors might be sensitive enough to detect this background, to distinguish between different models of cosmic origins. It's early days yet. The detectors are still being refined. The theoretical predictions are still being calculated, but the possibility is there. Within our lifetimes, we might have observational evidence for what came before the Big Bang. And then there are the puzzles within our universe that might point toward something prior. Dark matter, for instance. That mysterious substance that outweighs ordinary matter 5 to 1, but interacts only through gravity. We don't know what it is. We've never detected a dark matter particle directly, despite decades of searching. What if dark matter isn't a particle at all? What if it's a remnant, a vestige, a leftover from a previous universe that survived the bounce? Some models suggest this. The mathematics works, the observations fit. It's speculative, certainly, but no more speculative than many other dark matter candidates. Or consider the matter-antimatter asymmetry. Our universe is made almost entirely of matter, with only trace amounts of antimatter. But when matter and antimatter are created in particle physics experiments, they're always created in equal amounts. They annihilate each other, producing energy. If the Big Bang created equal amounts of matter and antimatter, as symmetry suggests it should have, why is there anything left? Why didn't everything annihilate, leaving only energy? Standard cosmology has answers to this question, involving subtle differences in how matter and antimatter behave, processes that occurred in the first second after the Big Bang. But these answers are complicated, fine-tuned, slightly unsatisfying. They work mathematically, but they feel incomplete. What if the answer is simpler? What if our universe inherited a matter-antimatter asymmetry from whatever came before? What if the bounce or the brane collision or the birth from quantum foam naturally produced more matter than antimatter, setting the stage for everything that followed? These are the kinds of questions that keep cosmologists awake at night, that drive them to build better instruments, develop more sophisticated theories, analyze data in new ways. Because the implications are profound. If we can figure out what came before the Big Bang, we'll have rewritten the most fundamental story we tell ourselves about reality. We'll have answered questions philosophers and theologians have been asking for millennia. We'll have pushed back the boundary of the unknowable, claimed new territory for human understanding. But there's a deeper question lurking here that we can't avoid any longer. Let's say we solve it. Let's say we determine definitively that our Big Bang was a bounce from a previous universe, or a bubble in eternal inflation, or a brane collision in higher dimensions. We'll have answered what came before the Big Bang, but we'll immediately face a new question. What came before that? If the previous universe bounced from an even earlier universe, where did that earlier universe come from? If eternal inflation spawns infinite bubbles, what started the inflation? If branes collide in the bulk, what created the branes in the bulk?
We can push the question back, but we can't eliminate it. Every answer generates a new why. Every explanation requires its own explanation. It's turtles all the way down, except we're running out of turtles and the ground we're standing on feels increasingly shaky. Some physicists embrace this infinite regress. They argue that the universe is eternal, has always existed, will always exist, and the question of ultimate origins is therefore meaningless. There is no first cause because there was no first moment. Time stretches infinitely far into the past, just as it stretches infinitely far into the future. This is intellectually consistent, but it leaves some people unsatisfied. It feels like giving up, like declaring defeat in the face of the ultimate mystery. Others suggest that the universe might be self-creating, that some kind of causal loop operates at the deepest level of reality. The universe creates itself through a bootstrap process, pulling itself into existence by its own quantum mechanical bootstraps. This sounds like logical nonsense, like lifting yourself off the ground by pulling on your own hair, but quantum mechanics is weird enough that such processes might actually be possible. Causality, that ironclad rule that effects must follow causes, might break down at the quantum level, at the moment of cosmic origin. There's also the possibility that we're asking the wrong question entirely. Maybe what came before is as meaningless as asking what's north of the North Pole. Not because time began with the Big Bang, but because causality itself might not apply to the universe as a whole. Causality is a feature of the universe, a relationship between events within space-time. But the universe itself, considered as a whole, might not be subject to causality. It might just exist, eternally, necessarily, without cause or reason. This touches on ancient philosophical debates about necessary versus contingent existence. Is the universe contingent, dependent on something else for its existence? Or is it necessary, existing by virtue of what it is? Philosophers have argued about this for centuries, generally in the context of arguing for or against the existence of God. Now physicists find themselves grappling with the same questions, armed with mathematics and data instead of pure logic, but facing the same fundamental mystery. Here's where science approaches its limits. Not because scientists aren't smart enough or lack good enough instruments, but because there might be questions that are inherently beyond the reach of the scientific method. Science operates by making observations, forming hypotheses, testing predictions. But if what came before the Big Bang is truly inaccessible to observation, if it left no traces, no evidence, no signatures in our universe, then science has nothing to work with. The question becomes purely philosophical, mathematical, speculative. Yet this hasn't stopped scientists from trying. Because sometimes the impossible becomes possible. Sometimes the untestable becomes testable. Sometimes nature provides windows into realms we thought were forever hidden. The cosmic microwave background was once pure theory, an untestable prediction. Now it's the most precisely measured fossil in the cosmos. Gravitational waves were fantasy for a century. Now we detect them regularly. The multiverse seems untestable today. But tomorrow? Next year? Next decade? And even if direct observation proves impossible, there's value in developing theories, in exploring possibilities, in mapping the logical landscape of what could be. Because understanding the range of possibilities constrains what our universe is and isn't. If we can determine that certain pre-Big Bang scenarios are impossible, that tells us something. If we can show that other scenarios inevitably lead to universes unlike ours, that tells us something else. Process of elimination is a powerful tool. Sometimes when you've eliminated the impossible, whatever remains, however improbable, must be the truth. But let's step back from the technical details, the competing theories, the ambiguous data. Let's think about what all this means for us, here, now, living our brief lives on a small planet, orbiting an average star, in an ordinary galaxy in what might be one bubble among infinite bubbles in an eternal multiverse. Does it matter? Should we care? Why should anyone care what came before the Big Bang? There are practical answers to this question. Understanding cosmic origins helps us understand fundamental physics. The extreme conditions of the very early universe test theories in ways impossible to replicate in laboratories. Every detail we learn about the Big Bang constrains models of particle physics, gravity, quantum mechanics. This has led to real technological advances. GPS satellites in particular rely on general relativity, Einstein's theory of gravity, which was developed partly to explain cosmological observations. You can draw a direct line from early universe physics to the smartphone in your pocket. But the real reason to care goes deeper than technology. It's about understanding our place in reality, about knowing our story, about answering the most fundamental questions conscious beings can ask. Where did we come from? Why are we here? What is the nature of existence itself? For most of human history, these questions were answered by religion, mythology, philosophy. Each culture had its creation story, its cosmogony, its explanation for why there is something rather than nothing. These stories served crucial psychological and social functions. They gave meaning, purpose, context. They connected individual lives to cosmic narratives. They made the universe feel comprehensible, even if the comprehension was metaphorical rather than literal.
Science offers a different kind of answer. Not metaphorical, but literal. Not comforting, but honest. Not designed to make us feel better, but designed to be true. And the truth that's emerging piece by piece, observation by observation, is stranger and more magnificent than any ancient myth. We're not the center of anything. We're not special in any cosmic sense. We appeared by accident in a universe that doesn't care whether we exist. And yet, we're part of something vast, ancient, perhaps eternal. We're how the universe examines itself, understands itself, marvels at its own existence. That's meaning enough. That's purpose enough. Not handed down from on high, not written in sacred texts, but discovered through careful observation and brilliant reasoning. We're the universe's way of knowing itself. And knowing that we came from somewhere, that there was something before the Big Bang, that reality is older and larger and stranger than we imagined, makes us more, not less. It expands our horizons. It deepens our connection to the cosmos. Consider the alternative. Imagine if the Big Bang really were the beginning, the absolute start with nothing before it. That would make our universe an isolated bubble, disconnected from anything else, floating in a void of true nothingness. We'd be alone in a way that's hard to articulate. The universe would be a finite thing, with finite age and finite history, bounded in time as surely as an island is bounded by ocean. But if something came before the Big Bang, if our universe is part of an eternal reality, connected to what came previously through bounces or brains or bubble formation, then we're not isolated. We're part of a continuum. The universe isn't an island, it's a wave in an infinite ocean, temporary in form but eternal in substance. We're citizens of eternity, made of eternal stuff, participating in an eternal process. This should change how we see ourselves, not as temporary accidents in a temporary universe, but as necessary expressions of eternal laws, inevitable consequences of infinite time and infinite possibility. Somewhere in the infinite past, universes formed and evolved and created the conditions that led to our universe. And our universe, in turn, might create conditions that lead to future universes. We're a link in an endless chain, a verse in an infinite poem, a note in an eternal symphony. Does this diminish the importance of our individual lives? Not at all. You are still unique, unprecedented, irreplaceable. The specific arrangement of atoms that constitutes you has never existed before and will never exist again. Your thoughts, your feelings, your experiences are yours alone. But you're also part of something larger. The atoms that make you were forged in stars, yes, but before that they existed in previous universes, passed through bounces, survived the Big Bang, assembled into the complex structures that allow consciousness to emerge. You contain multitudes, as Whitman said. But more than he knew, you contain eons. You contain eternities. You are made of material that predates the Big Bang, that survived cosmic compression and expansion, that has been recycled through countless stars and planets, and perhaps countless universes. Every breath you take contains atoms that were once part of dinosaurs, trees, ancient humans, primordial seas, early Earth, the solar nebula, dying stars, and before all that, previous cosmic incarnations were only beginning to glimpse. This is the new cosmology. Not a story of creation from nothing, but a story of eternal transformation. Not a universe with a beginning and an end, but a universe that has always existed and always will. Changing form, but never disappearing. Evolving, but never beginning. It's a cosmology that makes us both smaller and larger. Smaller because we're not central, not special, not the point of it all. Larger because we're ancient, eternal, connected to the deepest structures of reality. And we're only beginning to understand it. The theories are young, rough, incomplete. The data is sparse, ambiguous, open to interpretation. We're in the early stages of a revolution in cosmology as profound as any that came before. In a century, in a decade, perhaps even in a year, we might have answers that seem impossible today. New instruments might detect unambiguous signals from before the Big Bang. New mathematics might unify the competing theories into one elegant framework. New observations might eliminate whole classes of models, leaving only one standing. Or we might find that reality is even stranger than we currently imagine, that our best theories are wrong in ways we haven't yet realized, that the truth is hiding in a direction we haven't thought to look. Science has surprised us before. It will surprise us again. The history of cosmology is a history of beautiful theories murdered by ugly facts, of impossible observations that became routine, of mysteries that deepened before they resolved. But this is the beauty of the scientific process. We don't need to get everything right immediately. We can be wrong, learn, adjust, improve. Each generation builds on the work of previous generations, standing on the shoulders of giants to see further, to understand deeper, to push back the boundaries of the unknown a little bit more. The scientists working today on pre-Big Bang cosmology are continuing a tradition that stretches back to the first humans who looked up at the sky and wondered what those lights were, where they came from, what they meant.
And perhaps, in some distant future, on some distant planet, in some distant universe that hasn't been born yet, descendants of humanity, or their alien equivalents, will look back at our era and smile at our primitive understanding. They'll know what came before the Big Bang with the same certainty that we know the Earth orbits the Sun. Our tentative theories will be historical curiosities, quaint early attempts to understand mysteries that seem obvious from their perspective. They'll have instruments we can't imagine, mathematics we haven't invented, observations we can't yet make. But they'll be building on our work, using our data, reading our papers, standing on our shoulders. That's how knowledge grows. Not through sudden revelations or divine inspiration, but through incremental progress, careful observation, brilliant insight, and occasional luck. We're part of that process. We're contributing to an understanding that will outlast us, that will continue growing long after we're gone, that will, eventually, perhaps, answer the question we're asking today: what came before the Big Bang? The answer, when it comes, will likely be stranger than we expect. It always is. Reality has no obligation to match our intuitions, to fit our preconceptions, to make sense in human terms. The universe wasn't created for our understanding. We had to evolve the capacity to understand it, had to develop mathematics and instruments and theories that could map its contours, probe its depths, reveal its secrets. And every time we think we've got it figured out, reality shows us something new, something unexpected, something that forces us to revise everything we thought we knew. This is frustrating, but it's also thrilling, because it means there's always more to learn, always deeper mysteries to explore, always new frontiers to cross. The question of what came before the Big Bang seemed forbidden, unanswerable, beyond the reach of science. Now it's an active area of research, with competing theories and potential observations and real data. What seemed impossible became possible. What seemed unknowable became knowable. What else might we achieve? What other mysteries might we solve? What other questions might we answer? The history of science suggests that our current understanding, sophisticated as it seems, is just another step on an endless journey. We're not close to a final theory of everything. We're not near the end of physics. We're still in the foothills of understanding, with vast mountain ranges yet to climb. And that's good. That's exactly as it should be. Because the day we answer every question, solve every mystery, understand everything, is the day science dies. Curiosity needs fuel. Wonder needs mystery. The human mind needs challenges to overcome, puzzles to solve, horizons to reach. The universe, in its infinite generosity, provides exactly what we need: endless complexity, bottomless depth, infinite questions leading to more questions. So what came before the Big Bang? We don't fully know yet, but we're working on it. We're making progress. We're gathering clues, building theories, designing experiments. And one day, perhaps soon, perhaps in our lifetimes, we'll have an answer. Not a speculation, not a guess, but a solid, observationally confirmed understanding of what reality was like before our universe began. When that day comes, it won't be the end of the story. It will be the beginning of a new chapter, one filled with new questions, new mysteries, new horizons to explore. Because that's the nature of knowledge. The more you learn, the more you realize you don't know. The more you understand, the more you see how much remains to be understood. The circle of light grows, but so does the circumference of darkness it borders.
This might seem depressing, an endless task with no final answer, but it's actually liberating. It means we'll never run out of things to discover. We'll never exhaust the universe's capacity to surprise us. We'll never reach a point where there's nothing left to learn. The cosmos is endlessly fascinating, bottomless mysterious, infinitely rewarding to those who study it with patience and humility. And we're privileged to live in a time when one of the deepest mysteries is beginning to yield its secrets. Our ancestors wondered about cosmic origins, but they lacked the tools to investigate. Our descendants might consider the questions solved, obvious, elementary. But we're living through the revolution, the period when what was unknown becomes known, when what was impossible becomes possible, when what was forbidden becomes accessible. We're witness to something extraordinary, the rewriting of the universe's origin story, the discovery that there was something before the beginning, the realization that reality is older, larger, stranger, more magnificent than we imagined. We're living through a pivotal moment in humanity's intellectual history, comparable to the Copernican revolution, or the development of quantum mechanics, or the discovery of DNA structure. And the story is still being written. The data is still coming in. The theories are still being refined. The debates are still raging. We don't know how it ends. We don't know which theory will prevail. We don't know what surprises await us in the next generation of observations. But we're here, now, watching it unfold, participating in the greatest detective story ever told, the investigation into reality's deepest secrets. What came before the Big Bang? Something? Something real? Something physical? Something that left traces we can potentially observe? Something that connects our universe to a larger reality? A deeper story? An eternal process? Something that makes us part of an infinite tapestry, woven from threads that have always existed and always will?
That's the answer that's emerging from the data, from the mathematics, from the careful work of thousands of scientists across decades of research. It's tentative, it's incomplete, it's subject to revision, but it's pointing in a clear direction. The Big Bang was not the beginning. Something came before, and that something might be observable, testable, understandable. We stand on the threshold of a new understanding, looking back beyond the Big Bang into territory we thought was forever forbidden. We're using the most sophisticated instruments ever built, the most advanced mathematics ever developed, the most refined theories ever conceived, and we're starting to see, dimly, uncertainly, but unmistakably, what lies beyond the supposed beginning. It's the universe, always the universe, eternal, boundless, infinite in creativity and possibility, expressing itself in forms that rise and fall, appear and disappear, but never truly beginning, never truly ending, just continuing, forever, in an endless dance of creation and destruction, expansion and contraction, birth and rebirth. We're part of that dance, not separate observers, but participants, made of the same stuff, following the same laws, expressing the same eternal patterns. Every atom in your body has danced this dance countless times before, and will dance it countless times again. You are temporary, yes. Your current form will not last, but the essence of what you are has always existed and always will, in one form or another, across universes and eons and eternities. This is the new cosmology. This is the answer, incomplete as it is, to the question of what came before the Big Bang. Not nothing, not a singularity, not a beginning, but a continuation, a transformation, a phase transition in the eternal life of the cosmos. We came from something. That something came from something else, and so on, forever, without end, without beginning, without ultimate explanation. It's unsatisfying in some ways. We want first causes, ultimate answers, final truths. But reality doesn't owe us that satisfaction. Reality is what it is, regardless of our preferences. And what it is, apparently, is eternal, boundless, infinite in both directions of time, without beginning or end, without ultimate cause or final purpose. Just existing, necessarily, inevitably, eternally. We're learning to be comfortable with that. Learning that not every question has an answer, that not every mystery has a solution, that some things just are. The universe exists. It has always existed. It will always exist. It didn't begin. It won't end. It just is, was, will be. Timelessly, eternally, necessarily. And we're part of that. Not separate from it, not imposed upon it, not created to observe it from outside. We're it, observing itself, understanding itself, marveling at its own existence. We're the universe's self-awareness, its consciousness, its capacity for wonder. In us, reality becomes aware of itself, contemplates its own nature, asks its own questions about its own origins. What came before the Big Bang? The same thing that came after it. The same thing that's happening now. The universe, eternal and boundless, expressing itself in infinite forms, following laws that have no beginning, embodying patterns that have no end. We're one such expression, temporary in form but eternal in essence, unique in configuration but universal in substance. This is the deepest truth cosmology has to offer. Not a creation story with a beginning, not an ending story with an apocalypse, but a continuity story, an eternity story, a story without first page or last. We're a chapter in that story, a sentence, a word, a letter. But the story has always been there, and always will be. It's the only story there is. The eternal story of the eternal universe, told and retold in infinite variations, expressed and re-expressed in boundless forms. And we're learning to read it, learning the language it's written in, learning the grammar of physics, the vocabulary of mathematics, the syntax of natural law. We're deciphering the text, understanding the narrative, following the plot as it unfolds across cosmic time and cosmic space. We're readers and characters both, observers and participants, students and subject matter.
What a privilege that is. What an extraordinary circumstance. To be alive at a time when these questions can be asked and potentially answered. To have the tools, the knowledge, the observations necessary to peer beyond the Big Bang and see what came before. To realize that we're part of something eternal, something vast, something infinitely complex and infinitely simple at once. This is what the data is telling us. This is where the mathematics is pointing. This is what the theories are suggesting. Something came before the Big Bang. Something real, something physical, something that left its mark on our universe in ways we're only beginning to detect and understand. The mystery isn't solved yet, the question isn't fully answered, but we're closer than we've ever been. We're making progress. We're peeling back the layers of the greatest mystery ever contemplated. And underneath those layers, we're finding not emptiness, but fullness. Not nothing, but everything. Not a beginning, but a continuation. Not an explanation, but a deeper mystery that demands its own explanation. The universe is revealing itself to be richer, stranger, more magnificent than we imagined. Not created, but eternal. Not bounded, but infinite. Not simple, but complex beyond comprehension. We're children of this eternal universe, made of its eternal substance, thinking its eternal thoughts. We're how it knows itself. And what it's revealing to us, through patient observation and careful reasoning, is that it has no beginning, no end, no ultimate origin. It simply is, has always been, will always be. And we're part of it forever. That's the answer to what came before the Big Bang. Everything, nothing. Eternity expressing itself in time. Infinity expressing itself in space.
the same universe we inhabit now, in different form, following the same laws, embodying the same patterns, dancing the same eternal dance. Before the Big Bang was another universe, and before that another, and before that another, stretching back without beginning, stretching forward without end. We're learning to live with that, learning to find meaning in an eternal universe, learning that significance doesn't require cosmic centrality, that purpose doesn't require divine intention, that our lives can matter even in an infinite context. Because we're here, we exist, we're aware, we're capable of understanding, of love, of joy, of wonder. That's meaning enough. That's purpose enough. And knowing that we come from something eternal, that we're made of something eternal, that we're part of something eternal, doesn't diminish us. It elevates us. It connects us to the deepest reality there is. We're not accidents, we're necessities, not random but inevitable, not meaningless but meaningful in ways that transcend human purposes and human understanding. This is the gift that cosmology offers. Not comfort, perhaps, not easy answers, not the reassurance of a beginning and a purpose handed down from above, but something better. The truth, the real story, the actual nature of reality as best we can determine it through observation and reason. And that reality is magnificent beyond words, vast beyond comprehension, eternal beyond time. We stand at the edge of understanding, looking back beyond the Big Bang, seeing dimly what came before, knowing that what we see is only the beginning of understanding. There are layers beneath layers, mysteries within mysteries, questions that lead to more questions. But we're asking them, we're investigating them, we're making progress. And one day we'll know. Not everything, perhaps, not the ultimate answer to every question, but we'll know what came before the Big Bang. We'll understand how our universe fits into the larger reality. We'll see ourselves clearly as what we are, temporary expressions of eternal substance, brief patterns in infinite possibility, conscious nodes in the universe's network of self-awareness. What came before the Big Bang? We're finding out. And the answer is changing everything.
The mathematics alone should terrify us, not because it's incomprehensible, though much of it is, but because of what it implies when we follow it to its logical conclusions. When physicists first started calculating what happens to information in a bouncing universe, they expected erasure, complete annihilation. The compression should destroy everything, they thought, turn structure into chaos, patterns into randomness, meaning into noise. Like crushing a book until the letters blur into pulp, until the story becomes unrecoverable, until nothing remains but undifferentiated substance. But the equations said otherwise. They whispered something unsettling. Information, it seems, is more stubborn than matter, more persistent than energy. In certain models of cosmic bounce, quantum information can survive the compression phase, encoded not in particles or fields, but in the geometry of spacetime itself. Think of it like a hologram, where the entire image is encoded in every fragment, where destroying part of it doesn't destroy the information, merely reduces the resolution. The universe might work the same way. Compress it down to the Planck scale, squeeze it through the bottleneck of maximum density, and the information doesn't disappear. It persists. It waits. And when expansion begins again, it unfolds, like a compressed file extracting itself, rebuilding structure from mathematical memory. This has staggering implications. If information survives the bounce, then causality extends backward indefinitely. Events in the previous universe influence our universe. Not directly, not mechanically, but through subtle biases in probability, slight preferences in quantum fluctuations, delicate tilts in the distribution of matter and energy.
We might be living in a universe whose initial conditions were predetermined, not by divine will or conscious design, but by the final conditions of the universe that came before. Predetermined. Let that word settle. Does that mean our universe is deterministic after all? Does quantum randomness dissolve into deeper necessity? Not quite. The information that survives the bounce isn't complete. It's degraded, filtered, transformed by the extreme physics of the transition. Think of it like photocopying a photocopy of a photocopy. Each generation loses fidelity, details blur, fine structure vanishes. Eventually, you're left with general patterns, but not specific configurations. So the previous universe constrains ours without determining it. It sets boundary conditions without dictating outcomes. It influences probabilities without eliminating chance. We're partially free, partially constrained, dancing in a space of possibilities that was shaped by what came before, but not entirely defined by it. The past reaches forward, but its grip loosens with each cosmic cycle, each iteration, each bounce. Unless time itself is the illusion we've always suspected it might be. This is where the conversation becomes genuinely disturbing, where solid ground turns to quicksand beneath our conceptual feet. Multiple approaches to quantum gravity suggest that time as we experience it doesn't exist at the fundamental level. It's emergent, derived, a useful approximation that appears when you look at the universe from a certain perspective, at a certain scale, but not a feature of ultimate reality. At the deepest level, there might be no time at all, no before, no after, no flow from past to future, just a timeless mathematical structure, eternal and unchanging, from which our experience of temporal flow somehow emerges. How can this be? How can time not exist when we experience it so viscerally, so constantly, so unavoidably? The answer might lie in entanglement, that spooky quantum connection that Einstein famously distrusted. When quantum systems become entangled, their properties become correlated in ways that defy classical explanation. Measure one particle and you instantly know something about another particle, even if they're separated by vast distances. The correlation exists outside of space and time, or rather, before space and time at a level where those concepts haven't yet emerged. Some physicists propose that time emerges from entanglement itself. As quantum systems interact and become entangled with their environment, they create records, memories, histories. These records accumulate, building up a sequence of correlations that we experience as temporal flow. Time isn't flowing, we're just moving through an ever-growing network of entangled states, and our consciousness interprets this movement as temporal progression. The past exists as a vast web of quantum correlations. The future exists as regions of configuration space we haven't entangled with yet. In this view, asking what came before the Big Bang is asking the wrong question. It's like asking what's south of the South Pole when you're standing at the equator. The question assumes a frame of reference, a coordinate system, a way of organizing reality that breaks down when you approach the extremes. Before the Big Bang, there might not have been time as we understand it. There was something else, a quantum superposition of all possible times, a timeless state from which time crystallized, like ice forming from water, a phase transition in the fundamental structure of reality. But let's return to something more concrete, something we can potentially test. The James Webb Space Telescope, that magnificent instrument hovering at the second Lagrange point, has been peering deeper into cosmic history than any telescope before it. It's seeing galaxies that formed only a few 100 million years after the Big Bang, galaxies that shouldn't exist, that formed too quickly, that grew too massive for the time available. Standard cosmology struggles to explain them. The models predict smaller, dimmer, more primitive structures at these early epochs. Yet there they are, bright and massive and structured, staring back at us like anomalies in history.
What if they're not anomalies at all? What if they're evidence? signatures of pre-Big Bang structure that seeded galaxy formation earlier and more efficiently than random quantum fluctuations could manage. If the bounce preserved information, if patterns from the previous universe influenced the distribution of matter in ours, then galaxies might form faster, grow larger, organize more quickly than they should in a universe starting from scratch. This is testable. Barely testable, admittedly. The signals are subtle, the statistics challenging, the alternative explanations numerous, but it's testable. Over the next decade, as more data accumulates, as more distant galaxies are cataloged, as the statistical patterns become clearer, we might be able to distinguish between a universe that started from pure randomness and one that inherited structure from what came before. The universe itself might testify in court, might provide evidence for its own deeper history. There's another probe, stranger and more speculative. Quantum vacuum fluctuations should, in principle, contain information about the structure of space-time at the Planck scale. The vacuum isn't empty. It's fizzing with virtual particles, quantum foam, microscopic wormholes, all the exotic phenomena that quantum gravity predicts. These fluctuations affect real particles, cause measurable effects like the Lamb shift and the Casimir effect. They're real, even if they're fleeting. Now imagine building a detector sensitive enough to analyze the statistical properties of vacuum fluctuations with exquisite precision. You'd be probing the structure of space-time itself, looking for patterns, correlations, asymmetries. If space-time has memory, if it carried information through the Big Bang or the bounce or the brain collision, that memory might be encoded in the quantum vacuum. It's like reading the grooves in an old vinyl record. The music is encoded in tiny variations in the surface. Similarly, the history of space-time might be encoded in tiny variations in vacuum fluctuations. We're nowhere near building such a detector. The technical challenges are immense, but they're not impossible. Not in principle, just extraordinarily difficult. And difficulty has never stopped human curiosity before. Someone, somewhere, is probably already working on it, sketching designs in notebooks, calculating signal-to-noise ratios, applying for funding from agencies that think they're insane. Let's consider another possibility, one that emerges from the intersection of cosmology and consciousness studies. This is controversial territory, intellectual quicksand where careers go to die, but it can't be ignored entirely. Multiple quantum theories suggest that observation, measurement, conscious awareness plays a fundamental role in determining reality. The famous measurement problem in quantum mechanics remains unsolved. Why does a quantum system in superposition collapse to a definite state when observed? What counts as observation? Does it require consciousness? Most physicists avoid these questions, focus on calculating predictions and comparing them to experiments. But a few brave souls venture into the philosophical thicket, and they've proposed something extraordinary. Perhaps consciousness isn't a byproduct of physical processes, but a fundamental feature of reality, as basic as mass or charge. Perhaps the universe requires observers to fully exist, and perhaps the Big Bang itself was a kind of observation, a moment when reality observed itself into existence. This sounds like mysticism, like word salad, like the kind of quantum quackery that sells books to credulous readers. But there's actual physics here, buried beneath the provocative phrasing. The Wheeler-DeWitt equation, which attempts to describe the quantum state of the entire universe, has no time variable. It's a timeless equation describing a timeless state. Yet we experience time. We observe temporal flow. Some interpretations suggest that our observation, our conscious experience, is what creates time, what transforms the timeless quantum state into the temporal classical reality we inhabit. If this is true, then the question of what came before the Big Bang becomes intimately connected to the question of consciousness itself.
Perhaps there were observers in the previous universe, consciousnesses that experienced, measured, collapsed quantum states, and when that universe bounced into ours, perhaps something of those observations persisted, encoded in the quantum state, influencing the probability distributions that gave rise to our universe's structure. We might be living in a universe that remembers being observed, even though the observers are long gone. This is speculation piled on speculation, theory built on conjecture, but it points toward a deeper unity, a connection between the largest scales of cosmology and the most intimate phenomenon of consciousness. Perhaps they're not separate at all. Perhaps asking about cosmic origins is asking about the nature of awareness. Perhaps understanding what came before the Big Bang requires understanding what it means to observe, to experience, to be. The entropy problem deserves more attention than it usually receives. The second law of thermodynamics states that entropy, disorder, always increases in closed systems. The universe is presumably a closed system. Therefore, entropy should always increase. This gives time its arrow, its direction, its asymmetry. We remember the past, but not the future, because the past was lower entropy, more ordered, more structured. Memory requires entropy gradients, causal chains, irreversible processes. But here's the puzzle. If the universe is eternal, if it has existed forever, why isn't entropy already maximized? Why isn't everything in equilibrium, uniform, dead? In an eternal universe with increasing entropy, we should have reached maximum entropy infinitely long ago. The fact that we haven't, that stars still shine and galaxies still swirl and life still thrives, suggests something is wrong with our assumptions. The bouncing universe offers one solution. Perhaps entropy resets at the bounce. The compression creates conditions of such extreme energy density that thermodynamic laws break down. Entropy isn't conserved through the transition. Each new universe begins with low entropy, allowing for structure formation, complexity, life. The arrow of time points forward in each cycle, but it resets with each bounce. Time becomes cyclical on cosmic scales, even though it's linear within each cycle. But this raises new questions. Where does the entropy go? How does it reset? What physical mechanism could violate the second law of thermodynamics, even temporarily? These questions lack satisfying answers. The mathematics is incomplete, the physics uncertain. We're probing the limits of our theories, finding the edges where known laws give way to speculation.
Alternative explanations exist. Perhaps our patch of the universe, our observable cosmos, is just a local low-entropy fluctuation in an eternally static maximum entropy background, like a snowflake forming in supersaturated air, structure crystallizing temporarily from chaos. This is the Boltzmann brain problem writ large. In an infinite, eternal, high-entropy universe, any configuration, no matter how unlikely, will eventually occur by chance, including configurations like our entire observable universe, complete with its low-entropy past, its apparent history, its convincing fossil record. The problem is that such fluctuations are far more likely to be small rather than large. It's more probable for a single brain to fluctuate into existence, complete with false memories of a coherent past, than for an entire universe to fluctuate into existence with a genuinely coherent history. If we're just fluctuations, we should expect to be minimal fluctuations. We should expect to observe ourselves as isolated consciousnesses with illusory memories, not as beings embedded in a vast, consistent, lawful cosmos. Yet, here we are, embedded, consistent, subject to laws that operate the same everywhere we look. This suggests we're not fluctuations. We're something else, something that requires explanation. And that explanation might involve what came before the Big Bang, might require understanding how our universe fits into a larger structure that solves the entropy problem without invoking infinite improbability. The holographic principle offers another avenue of exploration, another way to think about cosmic origins. This principle, emerging from black hole thermodynamics, suggests that all the information contained in a volume of space can be described by information on the boundary of that space, like a hologram where a two-dimensional surface encodes a three-dimensional image. The universe might encode all its information on a distant boundary, with our three-dimensional experience being a projection, a shadow, a derived reality. If the universe is holographic, then the Big Bang might be understood as a transition in the boundary description, not an event within the volume. What came before the Big Bang could be a different configuration of the boundary, a previous encoding, a prior information state. The bounce or collision or bubble formation would be surface phenomenon, changes in the boundary description that manifest in our experience as the death and rebirth of space-time itself. This perspective makes information conservation natural. Information encoded on the boundary persists through transitions in the bulk. The bounce doesn't destroy information because the boundary doesn't bounce. It evolves continuously, with the appearance of discontinuity being an artifact of how we project the boundary description into a volumetric experience. We think the universe ended and began again because that's how it looks from inside the hologram. But from the boundary perspective, nothing ended, nothing began. Just smooth evolution, continuous transformation, eternal information processing. Testing this is nearly impossible with current technology. The holographic boundary, if it exists, is presumably at the cosmic horizon, billions of light years away, receding from us faster than light due to cosmic expansion. We can't send probes there. We can't even observe it directly. But there might be signatures, subtle effects, deviations from standard predictions that reveal the holographic structure. Slight graininess in spacetime at the Planck scale, unexpected correlations in quantum entanglement patterns, maximum entropy bounds that differ slightly from what volume-based calculations predict. Researchers are looking, designing experiments, analyzing data, searching for the fingerprints of holography in everything from tabletop physics experiments to cosmological observations. It's painstaking work. Most attempts find nothing. But it only takes one positive result, one unambiguous detection, to revolutionize our understanding. Consider the role of dark energy in all this, that mysterious force accelerating cosmic expansion. We don't know what it is. Observations suggest it's a property of space itself, a constant energy density that doesn't dilute as the universe expands. But why does it have the value it does? The value is crucial. Slightly larger, and galaxies never form. Slightly smaller, and the universe recollapses too quickly for stars to evolve. We exist in a narrow window where dark energy is strong enough to dominate eventually, but weak enough to allow structure formation first. This fine-tuning bothers physicists. In a single universe with arbitrary initial conditions, such fine-tuning seems suspicious, suggesting design or incredible luck. But in an eternal universe with multiple cycles or multiple bubbles, fine-tuning becomes selection effect. Most universes have wrong values. We inevitably find ourselves in one of the rare universes with right values because wrong values don't produce observers.
Yet dark energy might also carry information about what came before. Its value could be determined by the final state of the previous universe, by the density of matter and energy at the moment of bounce, by the configuration of quantum fields during the transition. If we could calculate what dark energy should be based on different pre-Big Bang scenarios, we could test those scenarios against the measured value. The cosmological constant becomes a message from the previous universe, a numerical signature encoding information about pre-existing conditions. This is active research. Multiple groups are working on it. The mathematics is horrendously complex. The calculations require assumptions about physics at energies we'll never reach experimentally. But the approach is sound. Dark energy is observable. Its value is measurable. If that value depends on pre-Big Bang physics, we can use it to constrain theories, eliminate impossibilities, favor likely scenarios over unlikely ones. Neutrinos might also carry secrets too, those elusive particles that barely interact with normal matter. They were created in vast numbers in the first second after the Big Bang, formed when quarks and electrons were still interacting freely, when the universe was hot enough for weak nuclear reactions to proceed rapidly. Most of those primordial neutrinos still exist, cooled by expansion to nearly absolute zero, invisible to our detectors, filling space with a ghostly background. But what if some neutrinos are even older? What if neutrinos from the previous universe survived the bounce, mixing with the neutrinos created in our Big Bang? Their energy spectrum would be different, their distribution slightly anomalous, their properties subtly wrong compared to predictions based solely on post-Big Bang production. Detecting these pre-Bang neutrinos would be a direct observation of the previous universe, like finding fossils from an earlier age. The problem is detecting them at all. Neutrinos interact so weakly that trillions pass through your body every second without effect. Building detectors sensitive enough to catch neutrinos requires massive targets and incredible patience. Building detectors sensitive enough to distinguish between primordial neutrinos and pre-primordial neutrinos requires technology we haven't invented yet. But the principle is sound. The physics checks out. It's not impossible, just extraordinarily difficult. And difficulty, as we've established, is merely an engineering problem, not a fundamental barrier. Now consider the possibility that we're completely wrong about everything, that all these theories, elegant as they are just elaborate delusions, sophisticated mistakes, castles built on mathematical sand. Science has been wrong before, catastrophically wrong. The luminiferous ether, phlogiston, the steady-state universe. Each theory was supported by smart people, explained existing data, made testable predictions, and each was eventually overthrown by better theories that explained more data, made better predictions, unified previously disparate phenomena. What if the Big Bang itself is wrong? Not slightly wrong, not wrong in detail, fundamentally wrong. What if the expansion we observe has a completely different cause? What if the cosmic microwave background has a completely different origin? What if we're misinterpreting the evidence, seeing patterns that aren't there, constructing elaborate narratives to explain observations that have simpler, stranger explanations? This is the nightmare scenario for cosmologists, that decades of work, thousands of papers, entire careers built on the Big Bang framework are based on a misconception. That future generations will look back at our era the way we look back at medieval astronomy, with a mixture of admiration for the cleverness and pity for the fundamental wrongness. But here's the thing, even if we're wrong in interesting ways. Even if the Big Bang is eventually replaced by something else, the replacement will have to explain everything the Big Bang explains, plus additional phenomena it couldn't handle. Scientific theories don't get replaced by random alternatives. They get replaced by better theories that incorporate their successes while fixing their failures. Newton wasn't entirely wrong about gravity. Einstein's theory reduces to Newton's inappropriate limits. Similarly, whatever replaces the Big Bang will probably reduce to the Big Bang inappropriate limits, preserving its successful predictions while extending into new territory. So even our mistakes are progress. Even our wrong answers teach us something. Even theories that eventually fail contribute to the accumulation of knowledge, constraining the space of possible truths, eliminating blind alleys, pointing toward productive directions. We learn from success and failure both. The only true failure is not trying, not questioning, not pushing against the boundaries of the known. And we are pushing relentlessly, with instruments and mathematics and imagination, with billion-dollar telescopes and underground detectors and orbiting observatories, with equations scratched on whiteboards and simulations running on supercomputers and late-night discussions in faculty lounges. We're attacking the problem from every angle, with every tool available, driven by curiosity and ambition and the fundamental human need to understand. What came before the Big Bang? We still don't definitively know. But we know more than we did yesterday. We'll know more tomorrow than we know today. The curve of knowledge trends upward. The mysteries shrink, slowly, grudgingly, but perceptibly. Each generation inherits the work of the previous generation and builds on it, climbing higher, seeing further, understanding deeper.
And one day, perhaps soon, the answer will crystallize. Data will accumulate past a critical threshold. Theory will mature beyond speculation. Observation will confirm or eliminate hypotheses. And we'll know. Not with certainty, perhaps, not with absolute confidence, but with the kind of robust, evidence-based, multiply-confirmed understanding that constitutes scientific knowledge. When that day comes, we'll face new questions, deeper questions, stranger questions. Because that's how knowledge works. Each answer opens new mysteries. Each solution reveals new problems. The frontier never disappears. It just moves further out, into stranger territory, toward deeper truths. What came before the Big Bang? The answer is coming, and it will change everything we thought we understood about existence itself.
There's a more radical proposition lurking in the mathematics, one that most physicists whisper about in private, but rarely commit to paper. What if universes don't come from previous universes at all? What if they come from nothing, constantly, everywhere, through quantum tunneling? Not the nothing we previously discussed, seething with virtual particles and quantum foam, but a different kind of nothing. A nothing so absolute, so complete, that even the laws of physics don't exist there yet. A pre-geometric, pre-temporal, pre-causal void from which everything, including physical law itself, emerges through quantum processes we barely comprehend. Quantum tunneling allows particles to pass through barriers that classical physics says they shouldn't be able to cross. An electron can tunnel through a wall if the wall is thin enough and the quantum probabilities align correctly. We use this effect in technology, tunnel diodes, scanning tunneling microscopes. It's real, it's measurable, it's routine. Now scale it up, unimaginably up. Could an entire universe tunnel into existence from absolute nothingness? The mathematics says yes. Not easily, not commonly, but inevitably, given infinite non-time in infinite non-space. The probability is infinitesimally small for any given location moment, but with infinite opportunities, infinitesimal probabilities become certainties. Universes pop into existence like bubbles in boiling water, each one creating its own space-time, its own physical laws, its own arrow of time. In this scenario, asking what came before the Big Bang is genuinely meaningless, not because time began with the Big Bang, but because there was no before in any sense we can comprehend. The tunneling event creates time itself, creates causality itself, creates the very framework within which before and after have meaning. It's not that something came before, it's that before didn't exist as a concept until the tunneling created it. This should break your brain slightly. It breaks the brains of physicists who work on it. We're creatures of causality, beings who navigate reality by understanding cause and effect, action and consequence, past and future. The idea that causality itself has an origin, that it came into being rather than always existing, violates our deepest cognitive structures. Yet the mathematics is unforgiving. It suggests exactly this conclusion. Roger Penrose, the Nobel laureate who proved that singularities are inevitable in general relativity, has proposed something equally strange called conformal cyclic cosmology. His idea dispenses with bounces and tunneling entirely, replacing them with infinite expansion. In Penrose's model, our universe doesn't end in a big crunch, it expands forever, asymptotically approaching infinite size and infinite time. But here's the twist. In the far future, when all matter has decayed, when all black holes have evaporated, when nothing remains but photons and gravitons spreading through infinite space, the universe loses all sense of scale. Without massive particles, without clocks, without any way to measure distance or time, the infinitely expanded universe becomes mathematically identical to an infinitely contracted universe. The end and the beginning become the same state. The heat death of our universe is the Big Bang of the next universe.
not through bounce, not through tunneling, through mathematical equivalence, through conformal transformation, through a kind of cosmic recursion where the end loops back to the beginning without any discontinuity, any singularity, any violation of physical law. Penrose has claimed to have found evidence for this in the cosmic microwave background: concentric circles, rings of temperature correlation that suggest massive events in the previous eon, the previous cycle, collisions between supermassive black holes that released enormous amounts of gravitational energy that somehow propagated through the transition between eons and left marks in our sky. Other researchers dispute his findings. The statistics are contested. The patterns might be artifacts, but the idea is breathtaking in its elegance. Time becomes truly cyclic, each eon emerging from the ashes of the previous one, each Big Bang following from a previous universe's heat death forever. What does this mean for information? In Penrose's model, information doesn't survive between eons. It can't. The conformal transformation erases mass, erases scale, erases everything except the most abstract geometric relationships. The previous eon influences ours only through its largest structures, its most energetic events, its gravitational wave background. Everything else is lost. Every star, every planet, every civilization, every thought, every love story, all of it evaporates into the heat death and doesn't return. We're not connected to the previous eon through continuous causality. We're connected only through the faintest echoes, ghostly reverberations in the geometry of spacetime. Is this better or worse than eternal recurrence, than exact repetition? There's something poignant about it, something almost poetic. The universe doesn't repeat, it rhymes. Each eon is genuinely new, genuinely creative, genuinely unpredictable. Yet each eon emerges from a previous eon's ending, creating an endless chain of cosmic creativity, an eternal process of death and rebirth where nothing is preserved except the bare mathematical structure that makes existence possible. But perhaps we're still thinking too conventionally, too bound by assumptions we haven't examined. What if the universe is computational? What if reality is, at its deepest level, information processing? This isn't mysticism. It's a serious proposal emerging from quantum information theory, from the study of black hole thermodynamics, from attempts to understand why mathematics describes reality so perfectly. Perhaps mathematics doesn't describe reality. Reality is mathematics. Perhaps the universe is a vast computation, and what we experience as physics is just the rules of the computation manifesting in our observations. In this view, the Big Bang isn't a physical event, it's a computational initialization, a moment when the algorithms started running, when variables were assigned initial values, when the cosmic program began executing. What came before? Other computations, parallel computations, meta-computations that generated the rules of our computation. An infinite hierarchy of algorithmic complexity, each level emerging from deeper levels, each level hosting its own universes with their own physics.
This sounds like science fiction, like The Matrix, like simulation theory for people who've taken too many physics courses. But there's real substance here. The holographic principles suggest that the information content of any region of space scales with the area of its boundary, not its volume. That's consistent with reality being fundamentally two-dimensional, with our three-dimensional experience being a projection, a computed output. Quantum mechanics operates through discrete states and probabilistic transitions, remarkably like a computer program. Even the speed of light might be understood as a computational speed limit, the maximum rate at which information can propagate through the cosmic algorithm. If reality is computational, then the question of origins becomes a question of where the algorithm came from. Who wrote the code? Who pressed the start button? Or did the algorithm write itself? Somehow, through recursive self-reference, through strange loops of causation that create themselves. Gödel showed that mathematical systems can be self-referential. Hofstadter explored strange loops extensively. Perhaps the universe is the ultimate strange loop, a self-creating, self-executing, self-observing computation that has no external creator because it contains the process of its own creation within itself.
Your mind should hurt by now. That's appropriate. These ideas push against the limits of human cognition, strain our conceptual frameworks, demand that we think in ways evolution never prepared us for. We evolved to hunt, to gather, to navigate social hierarchies, to avoid predators. We didn't evolve to understand quantum cosmology or infinite regresses or self-creating algorithms. That we can think about these things at all, that we can even formulate the questions, is extraordinary. That we might answer them is nothing short of miraculous. Let's talk about symmetry breaking, because this might be where the real answer hides. The universe, in its current state, is full of asymmetries. Matter dominates over antimatter. Time flows forward, not backward. Space has 3 dimensions, not 4 or 2 or 11. The fundamental forces have different strengths, particles have different masses. But the deepest theories suggest that none of these asymmetries are fundamental. They're all emergent, arising from spontaneous symmetry breaking as the universe cooled after the Big Bang. Think of a perfectly symmetric state, like a ball balanced on top of a hill. It's unstable. The tiniest perturbation will cause it to roll down the hill in some direction. Once it rolls, the symmetry is broken. The ball picks a direction. The choice is random, but the breaking is inevitable. Similarly, the universe might have started in a perfectly symmetric state where all forces were unified, where all particles were massless, where all directions in space were equivalent, where even the distinction between matter and antimatter didn't exist. But this state was unstable. It had to break. And when it broke, it created all the structure, all the asymmetry, all the diversity we observe. Here's the key question. Did the symmetry breaking happen at the Big Bang? Or before it? If before, then the Big Bang inherited broken symmetries from the previous state. Our universe's properties were predetermined by how symmetries broke in whatever came before. But if the breaking happened at the Big Bang, if that moment was genuinely symmetric, then our universe's properties are random, contingent, one outcome among vast numbers of possible outcomes. Different symmetry breaking patterns would produce different physics, different particles, different forces, different universes. Some researchers propose that every possible symmetry breaking pattern is realized somewhere, somewhen, in some bubble or eon or brain. This is the landscape problem in string theory taken to its ultimate conclusion. String theory predicts something like 10 to the 500 possible vacuum states, each with different particle physics, different force strengths, different dimensionality. If all of them exist, if the multiverse contains all possible realizations of string theory's equations, then we're back to anthropic reasoning. We observe this particular symmetry breaking pattern because this particular pattern allows observers to exist. But there might be a deeper principle at work, something that determines not just whether observers can exist, but what kinds of observers are probable. Mathematical structures aren't all equally complex. Some are simple, elegant, minimal. Others are baroque, complicated, arbitrary. Perhaps there's a principle of mathematical naturalness, a tendency for reality to favor simpler structures over complex ones, more symmetric configurations over asymmetric ones. Our universe might be selected not just for compatibility with life, but for mathematical simplicity, for elegance, for economy of structure. This would be testable in principle. If we could calculate the relative simplicity of different vacuum states, different symmetry breaking patterns, different physical laws, we could predict which universes should be most common. Then we compare our universe to the prediction. If we're typical, it supports the naturalness principle. If we're atypical, it suggests something else is going on, some additional selection mechanism we haven't identified. The topology of space-time might matter too. Most people think of space as flat, or nearly so, extending infinitely in all directions. But space could have exotic topology. It could be multiply connected, like a torus or a Klein bottle. Travel far enough in one direction, and you might return to your starting point from the opposite direction. Or space might have handles, wormholes, tunnels connecting distant regions. These topological features wouldn't be visible locally, Space looks flat over small distances even if it's curved or connected globally, but they'd affect cosmology, influence the cosmic microwave background, create distinctive patterns in the distribution of galaxies.
If space has non-trivial topology, that topology might be inherited from what came before the Big Bang. The bounce or transition or birth might preserve topological features, even while erasing everything else. Topology is robust. It doesn't change under smooth deformations. You can stretch or compress or bend space, but you can't change its topology without tearing it, without creating singularities. So topological features are exactly the kind of information that might survive cosmic transitions, might carry through from previous universes, might encode evidence of pre-bang structure. Searches for non-trivial topology are ongoing. Researchers look for matching patterns in opposite directions of the sky, suggesting we're seeing the same structures from different angles because space wraps around. They look for unexpected correlations, for size limits on large-scale structures, for any hint that space is finite or multiply connected. So far, nothing conclusive. But absence of evidence isn't evidence of absence. The topology might be so large that the observable universe samples only a tiny portion, or the matching patterns might be too subtle for current instruments to detect. Or we might not be looking in the right way, analyzing the right statistics, asking the right questions. Consider black holes in this context because they might be more relevant than anyone suspected. Black holes are space-time regions so warped that nothing can escape, not even light. They contain singularities, at least according to general relativity, points of infinite density where physics breaks down. But we've already established that singularities are probably illusions, artifacts of incomplete theories. Quantum gravity should resolve the singularity, replace it with something else, something finite and describable. What is that something? One possibility is that black hole interiors are baby universes. Not metaphorically, literally. When a black hole forms, it might pinch off from our space-time and become an independent universe, expanding into dimensions we can't access, developing its own physics, its own structure, its own history. From outside, it looks like a black hole. From inside, it looks like a Big Bang. The two descriptions refer to the same object viewed from different perspectives. If this is true, then universes reproduce. They create offspring through black hole formation. Each black hole birth is a universe birth. And since massive stars inevitably form black holes, since galaxies likely contain supermassive black holes at their centers, since black holes are common features of cosmic evolution, universe creation is happening constantly, not once in infinite time, not through rare quantum tunneling, but regularly, frequently, as a normal part of stellar evolution. This has profound implications. It means universes aren't isolated accidents. They're part of a reproductive chain, a cosmic genealogy, an evolutionary process. Universes that produce many black holes have many offspring. Universes that produce few black holes have few offspring. Over many generations, the population of universes would be dominated by descendants of universes that were good at making black holes. And what's needed to make black holes? Stars. What's needed for stars? Matter, gravity, nuclear physics tuned correctly. What did those require? Physical constants set just right. So the fine-tuning of our universe might not be anthropic selection for life. It might be natural selection for black hole production. Life is a side effect, a secondary consequence, an accidental feature of universes optimized for something else entirely. We exist because black holes exist, and black holes exist because the universe evolved to produce them efficiently. It's natural selection all the way down, but selecting for reproduction, not for consciousness. Lee Smolin proposed this decades ago. It remains controversial. Many physicists think it's too speculative, too untestable, too reliant on unproven assumptions about black hole interiors. But it's testable, in principle. If universes evolve to maximize black hole production, we can calculate what such universes should look like. We can predict their physical constants, their particle content, their force strengths. Then we compare to our universe.
Close match supports the hypothesis. Poor match refutes it. Preliminary analysis suggests a reasonable match, not perfect, but reasonable. Our universe does seem roughly optimized for black hole production. Change the constants much in either direction, and you produce fewer black holes. But more work is needed, more detailed calculations, more precise predictions, more careful comparison to observation. The hypothesis might yet fail, or it might succeed spectacularly, giving us an evolutionary explanation for cosmic fine-tuning that requires no multiverse, no anthropic reasoning, no appeal to probability across infinite possibilities. Now we approach the deepest mystery of all, the question that underlies every question we have asked. Why do physical laws exist? Why does mathematics work? Why is there something rather than nothing? We've discussed what came before the Big Bang, but we haven't addressed why there is a Big Bang in the first place, why there is a universe at all, why reality obeys rules rather than being pure chaos. This might be the wrong question. It might be like asking why truth is true or why logic is logical. Some things might be necessary, tautological, incapable of being otherwise. Perhaps a universe without physical laws is a logical impossibility, a contradiction in terms. If something exists, it must have properties. If it has properties, those properties must behave consistently, must follow patterns, must obey rules. Physical laws aren't imposed on reality from outside. They're inherent in the very concept of existence itself. To exist is to follow laws. To follow laws is to be describable by mathematics. There's no alternative, no other possibility, no conceivable reality that lacks this structure. Or perhaps the laws themselves emerge, crystallize, evolve from initial chaos. In the first moments before symmetry breaking, before space and time fully separated, there might have been no definite laws, only probability clouds, quantum superpositions of every possible law, every conceivable physics. As the universe expanded and cooled, as symmetries broke and structure formed, the laws crystallized into their current form. Like water freezing into ice, with its specific crystal structure determined by random initial conditions, the universe froze into this particular set of physical laws determined by quantum fluctuations and spontaneous symmetry breaking.
In this picture, physical laws aren't eternal and unchanging. They're contingent and historical. They had to become what they are. They could have been different. In other universes, with different initial fluctuations, different symmetry-breaking patterns, the laws are different. Not just the constants, but the laws themselves. Different numbers of dimensions, different kinds of particles, different fundamental forces. Perhaps even different mathematics, different logic, different conceptual frameworks entirely. This is as far as physics can take us. Beyond this point lies pure philosophy, pure speculation, pure wonder. We can calculate back to the Planck time, the first moment when our equations still make sense. We can theorize about what came before, about bounces and branes and quantum tunneling and conformal cycles. We can search for evidence, look for signatures, hope for observations that distinguish between competing models. But we can't explain why there's anything to calculate about in the first place. We can't derive existence from non-existence using logic alone. We can't prove that reality is necessary rather than contingent. Perhaps we're not supposed to. Perhaps there are questions without answers, mysteries without solutions, limits to knowledge that can't be transcended. Not because we're not smart enough, not because our instruments aren't sensitive enough, but because the questions themselves contain conceptual confusions, hidden contradictions, implicit assumptions that break down under scrutiny. Or perhaps the answer is simpler than we think. Perhaps existence is its own explanation. Perhaps reality doesn't need a reason to exist any more than mathematics needs a reason to be true. Perhaps the deepest truth is that being is more fundamental than non-being, that something is more natural than nothing, that existence is the default state,
and non-existence is the impossible anomaly. We stand now at a threshold. For the first time in human history, we have the tools to probe cosmic origins more than with speculation and mythology. We have telescopes that peer into the first moments of universal expansion. We have detectors that register gravitational waves from colliding black holes billions of years ago. We have mathematics sophisticated enough to describe quantum spacetime, to model bouncing cosmologies, to calculate the properties of brane collisions and bubble formation. We have theories that make testable predictions, that rise or fall based on observations, that connect cosmic origins to particle physics to quantum mechanics in webs of mutual constraint. The answer to what came before the Big Bang is emerging, not from any single observation or any single theory, but from the convergence of many approaches, many instruments, many brilliant minds attacking the problem from different angles. Some approaches will fail. Some observations will prove misleading. Some theories will be abandoned. But slowly, incrementally, inexorably, the picture is sharpening. The vague outlines are becoming distinct features. The speculation is crystallizing into knowledge. And what we're learning is this: the Big Bang was not the beginning. Something came before. That something was real, physical, governed by laws we're beginning to understand. It left traces we can potentially observe. It influenced our universe's structure, its properties, its evolution. We're connected to it through causality, or information, or mathematics, through chains of connection that span the supposed beginning of time. Whether that something was a previous universe that bounced, a quantum fluctuation in eternal inflation, a brane collision in higher dimensions, a conformal continuation of a previous eon, a computational initialization, or something stranger still, we don't yet know with certainty. But we know it was something. We know nothing didn't become something spontaneously and magically. We know reality is older, deeper, more complex than the traditional Big Bang narrative suggests. This is the revolution we're living through, the expansion of cosmic history beyond its supposed beginning, the realization that our universe has a prehistory, a context, a genealogy extending into territories we previously declared off-limits. We're not citizens of a universe that started 13.8 billion years ago. We're citizens of a cosmos that might be eternal, that certainly predates our local Big Bang, that connects us to structures and events and processes far beyond our cosmic horizon. Does this diminish us? Make our existence less meaningful? Strip away the last vestiges of cosmic significance? Only if we measure significance by centrality, by uniqueness, by isolation. But significance comes from connection, from participation, from being part of something larger than ourselves. And we're part of something incomprehensibly larger. We're embedded in a reality that's ancient beyond imagining, vast beyond comprehension, complex beyond calculation. We're how that reality knows itself, how it becomes self-aware, how it contemplates its own existence. That's meaning enough for any species, for any civilization, for any conscious beings anywhere in the eternal cosmos. We're the universe's eyes, its mind, its capacity for wonder. Through us, reality examines itself and finds itself magnificent. Through us, the eternal cosmos becomes aware of its own eternity. Through us, existence celebrates its own existence. So what came before the Big Bang? Everything that made us possible. Everything that made existence possible. Everything that connects us to the deepest structures of reality. Not nothing, not a singularity, not a beginning, but a continuation of something eternal, something necessary, something that has always existed in one form or another, and always will.
We're learning to read the cosmic story.
learning to decipher the signatures written in ancient light and quantum fluctuations and gravitational waves, learning to see past the Big Bang into the deeper history beyond. And what we're discovering is that we're not newcomers to reality. We're made of ancient stuff, participating in ancient processes, connected to ancient events that stretch back before time itself began. This is our answer. Incomplete, uncertain, developing, but real. This is what decades of observation and calculation and brilliant insight have revealed. The universe is older than we thought. Reality is larger than we imagined. Existence is stranger and more wonderful than any creation myth ever proposed. And we're part of it. We're connected to it. We're expressions of it. What came before the Big Bang? We did. Not personally, not individually, but essentially. The stuff we're made of, the laws we follow, the patterns we embody, all of it existed before, will exist after, exists eternally in the deep structure of the cosmos. We're not separate from cosmic origins. We're continuous with them. We're the universe contemplating its own birth, looking back beyond its own beginning, discovering that there was no beginning, only eternal transformation. And in discovering this, we transform ourselves. We become a species that knows its own deep history, that understands its place in eternal reality, that sees itself clearly as what it truly is, a way for the cosmos to know itself, a method by which eternity becomes conscious, a process through which existence celebrates its own impossible, necessary, eternal presence. That's the answer. That's what came before the Big Bang. Everything. Everything that matters. Everything that made us possible. And we're just beginning to understand how profound and beautiful and terrifying that answer truly is.